the steps that I'm going to go through. So, well, first of all, okay, just give you some literature that you can, you know, study further if you are interested in this subject. So the for all time, you know, the classical book by Zakharov, Lvov, and Falkovich, who is, you know, from a person who did pioneering contributions in the field, Vladimir Zakharov, and his other people who, Viktor Lvov, Gregory Falkovich, who also done some work on it, quite significant contributions. So my book is much more recent, so which was based on a lecture course, and as a result was more sort of aimed at more pedagogical, including problems and solutions, and also some new applications, some updates, you know, that existed at this time, which was quite a big expansion of the number of applications since the book of Zakharov. Okay, as well as, you know, there's some, you know, aiming at reaching out toward mathematicians, spelling some assumptions and steps very clearly, so that mathematician who usually say, I don't understand anything, so can you please go slowly, step by step, and, you know, tell me what you're exactly doing and assuming, right? So I was trying to do this as much as I can, because I'm not a mathematician myself, I'm a theoretical physicist. Okay, now the book, the collection of reviews, the advances in wave turbulence, okay, was aimed more at experimental works and you know, both observational and laboratory experiments. Okay, so with some outlook on how to proceed further with experiments, also contains some a introductory review by Alan Newell, who is also made great contributions in the field. Okay, and finally, okay, so it's probably most recent paper, which is kind of a mini review. This is aimed at a very introductory, as a very introductory level reading. So you might, if you don't know anything about that, you might want to start with that. And that's quite concise, quite short. Okay, so what is wave turbulence? We need to first of all understand what exactly we're going to be talking about, right? So, I mean, there's a certain confusion in terminology, right? So I prefer to think of wave turbulence not as a theory. I prefer to think of it as a state of motion in continuous medium systems. So, so it's rather an object rather than a theory about the object. So the turbulence is a state, and name turbulence suggests a chaotic motion of chaotic So what kind of chaotic motion? So it must be characterized by presence of waves, obviously, right? Of a broad spectrum of randomly propagating waves. random waves interacting via nonlinearity. So you can see what are the key words here. So it must be broad spectrum. So it must be waves that large number of waves that span from small wavelengths to larger wavelengths and everything in between. Okay, so they have to be random. In a sense, if you think of these waves of wave packets, they have to be their directions of propagations, their positions, their phases must be random. Okay, and also it's important, these waves are nonlinear. So linear waves, as you know, it's superposition principle works, and so they don't see each other. A solution for many waves is just a direct sum of solutions for individual waves, right? So these waves will be interacting and exchanging energies. Okay. So now certain remarks. So so wave turbulence can be weak when waves are weak, weakly nonlinear waves or strong exponentially strong waves. So the theory is most vast bulk of the theory is for weakly nonlinear waves, so weak wave turbulence. So what are the main objects of that? Okay, develop a statistical closure for describing spectrum, evolution of spectrum of such waves. So this is called wave kinetic equation. So for the wave action spectrum, I'll explain what I mean by wave action and what's the difference between energy spectrum. Of waves. Let's derive that and obtain solutions of it. In particular, the most important solutions in theoretical physics are the scaling solutions, possessing a particular property of universality. So in this context, they're called scaling solutions. Kolmogorov. Zakharov. Spectra, KZ. So, and this is in analogy with the famous Kolmogorov spectrum. Of hydrodynamic turbulence. So, and I will explain to you later that actually, so this is precisely this kind of solutions, scaling solutions, that brought the name to the subject wave turbulence. Namely, turbulence is the key word, right? So why do I think of random waves as turbulence? Kinetic equations were derived before Zakharov. They were derived in the beginning of last century, right? Piles and Nordheim. Okay, but those people were interested mostly with equilibrium, statistical equilibrium solutions. Relay gene spectra, Bose-Einstein, Fermi-Dirac distributions, right? Kolmogorov-Zakharov spectrum is a non-equilibrium, strongly non-equilibrium spectrum, a state like in turbulence. So I will explain that. So it has many properties. It's characterized by the cascade of energy via scales rather than equipartition, equidistribution among the degrees of freedom. So they were. That's where Zakharov contribution lies as a kind of pioneering, groundbreaking stone. He found these solutions and showed that this is a class of non-equilibrium mechanical systems that is like turbulence, but it has advantages to classical turbulence that it's more accessible for theoretical treatment. So because it has some small parameters in the system which, like small nonlinearity, which are absent in hydrodynamic turbulence. So now I'll mention some applications. Applications and where in these applications if turbulence comes as a useful tool. So, as I mentioned already 1 second ago, that the kinetic equation, quantum kinetic equation, for weakly interacting Bose or Fermi gases. So famously introduced in the subject by Nordheim in 1928. So he did not derive it like we do it these days. He used the Fermi's golden rule principle. Okay, that was the most direct way to obtain such an equation. So this quantum kinetic equation actually has a classical limit. That is exactly wave kinetic equation. So where is it useful for the theory of BEC? In particular, if we deal with kinetic processes, like non-equilibrium processes of condensation, so transport properties in quantum systems. So this is perhaps for people who work in quantum mechanics, it's a very familiar object. You know, so the quantum kinetic equation. So the second application, so sound or phonons in anharmonic crystals. That is almost simultaneously with Nordheim, with just 1 year difference or whatever, potentially at the same time, was derived by Peierls. And he applied it to thermoconductivity of crystals. Classical, yes. Just the usual model of crystal as a periodic, the particles periodically, ions periodically connected with potentials. Phonons, this is with phonons. No quantized phonons, but there are phonons. Quantized actually here. So if you say occupation number much greater than 1, you get wave kinetic equation. So this he already, but that is combining the two, you can immediately derive the one for quantum case. Okay, so then plasma waves. And there's a huge number of different plasma waves, types of plasma waves, spanning over great number of great ranges of frequencies and so on. And so just to name a few, so this is Langmuir waves, ion sound waves, so MHD waves or Alfvén waves, magnetosound waves. So Whistler is drift waves, importantly. So the people, okay, so okay, I haven't got space here, but I'll write people here. So this is you know, I guess was brought in the area by Litvak in 1959, but from that in 60s, there's a great number of works just expanded. So Bedenov, Sagdeev, Zakharov, who who was a PhD student of Sergey. Okay, Kadam. So a lot of Russians. So this have application, very useful application for fusion plasma, and fusion. Let's say the confined and inertial. So confined fusion is confined by magnetic field, such as tokamaks, stellarators. So inertial, it is something that happens much quicker, different philosophy, such as laser beams hitting a target, or electron laser beams hitting a target, or electron discharge, which is very quick. Okay, and so this wave turbulence, they allow to understand and predict many different transport properties in plasma turbulence. And transport is very important for confinement, because that's how the goal is to transport brings particles and energy away from the device, from the center, so it kind of breaks the confinement, right? So the idea is to understand and make sure that we confine for a long enough time, and so on. Okay. So there's a huge number of applications which I'm not going to mention all, but I have to mention this. So water waves, of course, is the most sort of common example, and more you can visualize straight away. I mean, everybody saw the sea waves, right? And I don't know how well you realize or appreciate that this is a very complicated system to describe, actually, to describe distribution of energy among waves of different wavelengths. But it's very important for prediction of wave weather, for navigation. Okay. So navigation. For exploration at sea, oil platforms, where do you need to, shut your device, take your drill out, so if the waves are coming. Okay, and in general, for the transport properties of and between atmosphere and the ocean. That's a key ingredient in modeling the climate. So here, of course, Zakharov. That's precisely the example he used in his PhD thesis to derive spectrum that we know by the name Kolmogorov-Zakharov right now. Okay, so, well, internal waves. So a lot of work on it was done by Lvov, but now it is son Lvov, Yuri Lvov, with his collaborator Kurt Polzin. So in 2000s, I would say. although some previous work was done, but I mean, they really done a lot of work, and Kurt Polzin is observationalist. He's the best observationist for this kind of systems, waves. So how are they important? So these are the waves that are inside the ocean. They're due to stratification of the ocean, right? So they're kind of on the density interface, like thermocline. You know that there is about 100 meters of lighter water on top of the ocean than cooler below because of differences of temperature. So it's called thermocline. And on the interface of that, internally, there is very important waves. Also in the much deeper in the abyssal ocean. So how important they are? They're extremely important because they're thought to be responsible for mixing of of energy, thermal energy and density across the ocean. When your conveyor belt is going like that schematically, right? Okay. So you have something going on top of the ocean, okay, then comes to cooler area and sinks, right? And goes here at the bottom. But what brings it up? What brings it up? Okay, here it cools down and sinks. Here, something has to warm it up, but what warms it up at the bottom of the ocean? Nothing. So this means that it's a different mechanism of going up. So it's waves that mix the particles slowly and kind of in more or less random walk fashion, bring them up again at the top. So the it's called general circulation in the models of climate. And so this is mixing. Mixing mechanism. Okay. Well, the last one I'm going to mention I'd like to mention them all, but I'm afraid then I won't have time left to talk about the subject itself. So, but I'll mention just one last one, which I'm particularly excited about. This is wave turbulence and general relativity. And this builds on the fact that Einstein equations, field equations, are nonlinear, right? And that makes them very different from, say, Maxwell's equations, right, for electromagnetic field. And nonlinearity is precisely what we need to see wave interactions. And which waves are here? Of course, they are gravitational waves, right? So this was 2 years ago, a paper of Sébastien Gaultier and myself. 2017, we published it, and which we suggested as an alternative explanation of the accelerated expansion of the universe. So. So expansion of early universe, you know, there's inflation, right? So this inflation, this expansion happened somewhere early on, exponentially, and it's very hard to explain it without bringing in some hypothetical new fields, like instanton fields. So in this theory, we try to do it without that. It's a beautiful system, which is absolutely empty universe, vacuum. and the only thing that happens in this universe that it's actually disturbed initially. So it's corrugate. If you think of a universe as a sphere that is expanded, right? So it's a sphere with ripples on it, and these ripples make it expand very fast. Okay. So all right. Okay. So this enough with applications. So let's see. Actually, I forgot to notice where I started. Pardon? 11:40, right? So which means what half the lecture. Okay, so 30 minutes, right? No, 20. Yes, because it's a continuous. So I'll just stop wherever my time is up, and I'll continue. So okay, I'll just watch time here. Okay, so okay, 57. Okay. All right, so let's just get to the substance of it, and see what tools wave turbulence uses. And of course, I will start with weak wave turbulence, and maybe I will also finish with it, because that's weak wave turbulence is where things are more developed, and there's a lot more remains to be done to describe strong turbulence, right? Where waves can coexist and interact with coherent structures like vortices, like what Carla was suggesting in his talk. Is it waves or is it vortices? Most likely to be both, right? And they're interacting. Okay, not only waves interacting among themselves, not only vortices interacting among themselves, but also waves can affect vortex dynamics and vice versa. Okay, but that's that is of course, you know, a much more complicated subject, and we'll start with something simpler than that. So we will start with derivation. Of the wave kinetic equation. And then we will start with, because we are, you know, we have the most favorite equation in the school, right? And so this is a Gross-Pitaevskii equation, which I will call nonlinear Schrödinger equation. If you try to call this equation Gross-Pitaevskii equation to mathematicians, then toward the end of your lecture they say, why are you trying to confuse us and call NLS Gross-Pitaevskii equation? So this is one of the most universal equations. So I would probably argue is as universal as Navier-Stokes equation in terms of the number of applications and conceptual things we can understand on the conceptual level. So epsilon, I introduced just for convenience. Epsilon will be a number, which at some point I will just say it's much less than 1, because I'm going to deal with weak nonlinearity. And I'll say that psi is of order of 1. I could have just done it without epsilon, but then I would have to say psi much less than 1. But if I want to see explicitly the nonlinearity parameter, I just put that. That's usual. I can bring one into another by simple rescaling of psi. So, well, okay, it depends on the problem I'm considering. I might want to add here a trapping potential, right? U psi. Okay, well, I might want to use different type of nonlinearity. For example, in optics, they use saturating nonlinearity or non-local nonlinearity. For example, self-gravitating Bose gas. But this is the most basic nonlinear model. Okay, So the boundary conditions for me, because I will be concerned with waves, I will say that the boundary conditions are periodic. So, which means that that psi, okay, psi will be a function of the space, physical space and time, with physical space variable is on a d-dimensional torus of size L in all directions, meaning just periodicity in all of the directions. And as far as the dimensions are concerned, I will be only dealing with 2 and 3, because, as you probably know, in one dimension, the problem is integrable, and it's completely a different story. So everything that I'm considering here, it doesn't apply to 1D systems. So apart from some basic facts like this, so that I can write rewrite this equation in Hamiltonian form, with Hamiltonian representing the energy of the system, right? I integrate over the periodic box, okay. So this will be constant because of because it's its energy. And the energy consists of 2 parts. Okay, so it consists of the quadratic with respect to the field psi no linearity. Oh, one thing I of course should mention, but you of course know that. So this is the psi is a complex scalar field, right? So this is usually called free Hamiltonian, or this is called interaction Hamiltonian, right? So if I neglected that, I would just have free particles with dispersion relation omega equal to k squared, right? And this would makes them interact. So a weak wave turbulence applies when this part is less than that. But actually, I think I did something wrong here because I wrote Hamiltonian for the case epsilon equal to 1. Right? So I think to be consistent with that, I have to write epsilon here. And then you see that so weak wave turbulence theory works in situations where the second part of Hamiltonian is much less than the first part of Hamiltonian. And therefore, the energy mostly approximately equal to this part. Because we are dealing with waves, it's best to go to wave number representation. So we go to Fourier space. And that's precisely why I wanted the system to be periodic, so that Fourier transformers will define a series. Okay, so I say let me represent wave function as a sum of individual harmonics. And because of periodic boundary conditions, wave number will be on a lattice like this. So it will be, let's say it's 2 decays, right? So it will be on a grid of points right, kx, ky. So the distance between the points, as usual, because of periodicity, is 2 pi over size of the box. Right? So later on, we will want to take limit L to infinity to get to continuous case. So we'll get L to infinity, so delta k will get to 0. And so we'll have continuous wave number description. So for the inverse Fourier transform is of course okay. Of course, psi has to satisfy certain properties of existence of certain derivatives, but okay, we are physicists, we're not concerned with that. Everything is satisfied, right? So Fourier transform also can be defined with different normalizations, right? So the way I've chosen it here, so that it has a convenient infinite box limit. So this quantity is actually conserved, right? You can easily check that in the original equation by multiplying the original equation by psi conjugate, adding to its conjugate and integrating over periodic box. It's conserved not only in periodic box, it conserves with many other different boundary conditions, like decaying boundary conditions in infinite systems, or when psi goes to 0 at the walls somewhere in the finite system, so on. So this is invariant that is called the mass density. Well, okay. So this usually what you see here is called mass, right? And this, because I divided by volume of the box, so it's mass density, or mean mass density. So you can, for simplicity, call it mass, right? So it's mass. And so the reason I put here, so you see that it becomes in Fourier representation like that. L is not involved. And I will insist, when I take L to infinity limit, that this quantity remains finite, independent of L, right? So each time I increase the box size, my field, my coefficients should not change. So, I mean, not the coefficient should not change, but this sum should not change, right? Okay, so then what I'm going to do, I'm going to use this formula, right? I'm going to multiply my equation, NLS equation, by complex exponential and integrate with respect to x, so that I get equation for the Fourier coefficient, right? And if I do that, so now so let me just, briefly explain notations. So for brevity, I just, instead of writing psi of k1, I say it's psi1, okay, something forward, right? Then, and so for 2 and 3, the same. So delta 1 k2 3, so it's equal to, it's equal to 1 if k1 plus k equals to k2 plus k3, and it's equal to 0 otherwise. So this is a discrete delta function, right? So it's called Kronecker symbol. So these kind of things we can do, right? We know how to obtain sums like that out of nonlinear terms like this, right? Okay, if you don't, I mean, you can do a little homework yourself, right? And okay, in that equation, instead of psi's, right, 3 psi's, what you do, you substitute this in there, right? And then you have another integral because you integrate the whole equation like this. And then you will see that one integral you can take, right? You will be taking integral of the complex exponential, which will give you 0 all the time, unless your wave numbers satisfy this, right? Okay, so this is kind of a simple exercise. Now, so this is our equation that we'll be using as a starting point to derive equation for the wave action spectrum. Which is defined as nk. Okay, so n meaning n of k, and it's also a function of time, right? So it's defined as L over 2 pi to power d modulus of psi k squared. So, I mean, often you can see a definition like that without this factor. But as I said, I mean, if you want to take the, so to say, thermodynamic limit, so that the limit in L tends to infinity, so that this quantity remains constant, you got to do it this way. it also has a relation between continuous Fourier transform and a discrete Fourier transform Fourier series, right? Because in continuous, I would say, if I'm in continuous limit, so then nk would be defined like this. So I take psi k prime conjugate, and I would say it's nk delta of k minus k prime. So now this is Dirac's delta. And this is a continuous Fourier transform. It's not the same as a Fourier series. But if you make a correspondence from one to another, objects like delta function goes into precisely L over 2 pi over D, right? So when k equal to k prime, that is not defined, right? But in discrete case, it's defined. So it just getting bigger and bigger as L tends to infinity. Yeah. Okay. The very good question, which I will answer. I will postpone because I will precisely describe what averaging is made over. So I can tell you it's average over the phases of initial waves, of initial data. But that's a technical thing that we'll discuss, and whether this can be extended to other kind of averages. So first of all, okay, so linear approximation. Which, of course, corresponds to epsilon equal to 0 case, right? And in this case, okay, the sum there on equation at the top is equal to 0. And elementary, we have a wave solution of the form psi k equal to ak e to minus I omega kt. So omega k, which is equal to k squared, this is dispersion relation for this case. This is the frequency so wave frequency. So what kind of wave is it, right? I like to think of it as a de Broglie wave, right? Because there's other waves that Carlo already mentioned, sound waves that appear in this model, but they appear on background of pre-existing condensate, right? Here we consider epsilon close to 0. This means the equilibrium state for these waves is 0, so no condensate. You can consider that maybe you can, before you create condensate, you start with these waves and hope to grow mean density, right? So this is one of the concepts of non-equilibrium condensation in the system. Okay, so, all right, so perhaps then. Yeah, okay. Yes, okay, so maybe I've chosen the wrong normalization in the end. Yes. No, hold on. No. Mass, of course, goes to infinity. The mass in one periodic box. So, yes, okay. So, nk over here, you can see that, okay, so, well, let's work it out, right? So, this is going to be, so the total mass, n, is going to be sum of nk of 2 pi L d, right? So which in the continuous limit will go nk dk. Yeah, of course you can think of it as, right? Okay, so I guess I can take questions right now and yes? Okay, I guess that was no questions. This is mass density, you see? So because well, if you think of this as mass, right? In one periodic replica, so then you divide by the volume of it, so it becomes mean mass density, right? Yes, it's proportional to the number of excitations, right? Yes. So to talk about density, well, yes, it is density of excitations. I mean, you can see it here, right? So, but in discrete system, yes, if you think about it, okay, so the number of excitations. So the number of excitations, let's call it n. Okay, so that would be nk divided by h bar, right? So if the levels are spaced with h bar, if you're thinking of quantum systems, that's the correspondence, right? So that's a number of phonons at one level. So level with the momentum k, right? And then the energy of that would be correspondingly the usual no, it remains constant. Little n remains constant, yeah. Yes, well, you see, because you I put it here. You see, I put it here, right? So you see, so this is my n, right? Like this. Yes. Yeah. No, I want to take a limit so that it's constant, right? You see, the total mass tends to infinity because the boxes tends to infinity. But I want density. Okay, sure. Okay. Okay. So, thank you. except the theory is constructed in such a way, you kind of like